All right, here's your video for the remainder of Unit 5A, which includes topics 5.4, 5.7, 5.8, and 5.9, all related to reaction mechanisms. Each of these individual topics is a relatively short set of information material on things that you have to do with reaction mechanisms. My mindset, it was easier just to combine all four of these together and get through it all at once. You can see the interrelationships between all the things. So we'll start with elementary reactions. The chemical reactions, the chemical equations that we work with in class are just summaries of the actual chemical changes that take place. Chemical reactions are rarely as simple as single-step processes. Most chemical reactions take place in a sequence of smaller reactions called elementary reactions. The sequence of steps or elementary reactions is called a reaction mechanism. So the reaction nitrogen dioxide reacts with carbon monoxide to produce nitrogen monoxide and carbon dioxide is just a summary. That overall reaction actually takes place in two elementary steps. In step number 1, two nitrogen dioxide molecules react and form a single nitrogen trioxide and one nitrogen monoxide molecule. In elementary step 2, the nitrogen trioxide reacts with the carbon monoxide to produce nitrogen dioxide and carbon dioxide. These two elementary steps together are called the reaction mechanism. And again, when we summarize what takes place in the reaction mechanism, we get the overall reaction. In the first topic, in topic 5.4, all you have to do is, given the elementary steps, add them together to find the overall reaction. The process is similar to what we do in net ionic equations. We look for things that we have on both sides of the arrow, and we cancel them out. Our overall reaction will be what's left over. Now, unlike our net ionic equations, some things will cancel out completely, some things will not. The substances that cancel out completely are called intermediates. And in our example mechanism, the NO3, the nitrogen trioxide, is an intermediate. It appears as a product in the first step and then is consumed in the second. So let's go back to the elementary steps. Again, in step number 1, we see the nitrogen trioxide being produced. And then in step number 2, we see the nitrogen trioxide being consumed. If it appears as a product first and then is consumed in a later step, it is what we call an intermediate. Some substances will appear on both sides but only partially cancel out. And if that happens, they end up being written in our overall equation. These substances tend to appear on the reactant side first and then appear on the product side in a later step. These substances are classified as catalysts. Let me go back to the original one. Again, what we'd be looking for is something that is on the reactant side first and then appears on the product side later. And if we look, we have nitrogen dioxide here on the reactant side in elementary step number 1. And we have nitrogen dioxide here on the product side in elementary step number 2. Now this will only partially cancel out because there's only one here and there's two there. So only one of those will cancel, and there will be an NO2 that is left on the reactant side, as we see in our overall equation. But because it appears on the reactant side first and then again on the product side later, we would classify the nitrogen dioxide as a catalyst. Let's take a look at another example. And as we go through this example, we're going to summarize these three steps as an overall equation. And then we are going to identify the intermediates and the catalysts. So the first thing we got to do is look for substances that we find on both sides of the arrows. We have N2O2 on both sides of the arrows. Here it is on the product side. Here it is on the reactant side. We have N2O on the product side and the reactant side. So dinitrogen dioxide on both sides, dinitrogen monoxide on both sides. They do completely cancel out, and they appear on the product side before they show up on the reactant side. Both will appear on the product side before they appear on the reactant side. That makes those intermediates. The overall reaction is just what's left over. We have these two NOs, nitrogen monoxides, that we summarize as 2NO. And we have these two hydrogens that we summarize as 2H2. That completes the reactant side. On the product side, we have one N2 nitrogen that we put here. And we have two water molecules, H2O, that we summarize as 2H2O in our overall equation. This particular reaction does not have a catalyst. There is nothing that shows up on the reactant side first. So NO, nitrogen monoxide, shows up on the reactant side first, but it does not appear anywhere on the product side. We have hydrogen, H2, that appears first on the reactant side, but again, it does not appear anywhere on the product side. So there is no catalyst in this particular reaction. That, in a nutshell, is the first topic, 5.4. Now we move on to molecularity. This is the first of the topics in topic number 5.6. No, 5.7. And 5.7. Molecularity is the number of species that have to collide to produce the reaction indicated in the elementary step. So molecularity only applies to elementary steps. You never look at the overall reaction and decide what its molecularity is. Only at the individual steps. Molecularity is the sum of the coefficients on the reactant side of that elementary step of its equation. There are three types of molecularity: unimolecularity, which means one. In other words, the sum of the coefficients on the reactant side of that elementary step is one. There's bimolecular. Bi means two. So when you add up the coefficients on the reactant side of that elementary step, you get two. And there's termolecular, term meaning three. So in other words, when you add up the coefficients on the reactant side of that elementary step, you get three. For unimolecular, there's only one possibility. That is one reactant with a coefficient of 1. So when we look at this elementary step, dinitrogen tetroxide produces 2 nitrogen dioxides. Again, all we're looking at is the N2O4. All we're looking at is the dinitrogen tetroxide. There is only one reactant there. It has nothing in front of it, so the coefficient is 1. So the sum of the coefficients in that particular equation is 1. It is sometimes summarized as A produces products. In other words, one reactant, one molecule produces all the products. In bimolecular, we have two possibilities. We can have a single reactant with a coefficient of 2, as we do here. We only have one reactant, the NOCl. Its coefficient is 2. So the sum is 2. This is sometimes written as A plus A produces products. In other words, 2 molecules of the same reactant collide to produce our one product. The other possibility is having two reactants, each with a coefficient of 1, as we do here, the carbon monoxide and the nitrogen trioxide. We have two reactants there, nothing's in front of them, so the coefficient is 1. 1 plus 1 is 2, bimolecular. It's written very similar to the previous one, but this time it's A plus B produces products because we have two different reactants. Finally, there's termolecular. There's two possibilities there. You can have two reactants, one with a coefficient of 2, the other with a coefficient of 1, so we get the 2 plus 1 equals 3. As we do here, 2 nitrogen monoxide react with 1 oxygen. 2 plus 1 is 3. Sometimes written as A plus B produces products, so that you can see it's really 3 molecules that are colliding here. Thus, termolecular. And again, 2 A's because there's 2 in front of the NO. The other possibility is you have 3 reactants, each with a coefficient of 1, as we do in this equation. So a free hydrogen atom plus an oxygen molecule plus M produces HO2 plus M cubed. This is a strange reaction. I don't even know how to read it, honestly. It is an atmospheric reaction. It's the only example of one of these termolecular ones I could find. Again, summarized, A plus B plus C produces products because all 3 of these things are different. We can write rate laws for these elementary steps based on their molecularity. To do that, we just have to basically look at the reactants in our elementary step and write them as a rate law. Before we get into it, important note, you cannot use these when looking at the overall reaction. What I'm showing you now applies only to elementary steps. It doesn't apply to the overall reaction. What we're going to do is we're going to take the coefficients from each substance and write them as that substance exponent. So the format is rate equals K times whatever reactant A is to its coefficient, whatever the concentration of B is to its coefficient, and if there's 3, whatever the concentration of C is to its coefficient. The number of reactants you put in this rate law depends on the molecularity, the type of equation that you're looking at. If there's only 1 reactant, you would stop here. If there's 2 reactants, you would include both A and B. If there's 3 reactants, you would have to include all 3. So let's figure out the rate law for these elementary steps. They're not from the same equation, but they are elementary steps. So what we would do up here is we would write rate equals K times the concentration of our 2 substances. So it would be CO, no coefficient, so it would be to the first power. Then the NO3 in brackets for the concentration of NO3. Again, no coefficient, 1 as the exponent. For this one, there is only 1 reactant, so we would write rate equals K times the concentration of NOCl as a coefficient of 2, so it would be squared. They end up looking like this. So again, I'm just taking my reactants, putting them in the brackets, and I'm taking their coefficients and making those the exponents. If I have 2 reactants and there's 2 substances that go in my rate law, if I have just 1 reactant, there's only 1 substance that goes in my rate law. Now on to the next topic, rate determining steps. This is 5.8. In a multi-step reaction mechanism, the elementary reaction that determines the overall reaction rate is the rate determining step. The rate determining step is always the elementary reaction with the slowest reaction rate. In AP Chemistry, they make identifying the rate determining step super simple. They're going to use the words fast and slow. The slow one is the slow step. The fast one is the fast step. As simple as that. So in this, the first step is the rate determining step. There may be some rare instances where they give you the value for the rate constant for all the steps. You just have to remember the one with the highest rate constant is the fastest step. The one with the lowest rate constant is the slowest step. And you can write fast to slow based on that. Because the rate determining step determines the rate of the overall reaction, the rate law for the overall reaction is the same as the rate law for the rate determining step. So just a few minutes ago, I told you you cannot use the rate law for an elementary step to write the rate law for an overall reaction. Well, yeah, that's true if you're looking at these as individual topics, but since we're wrapping them all up into one, if the rate determining step is the first step in the reaction mechanism, its rate law will also be the rate law for the overall. So here are our steps. The first step is the slow one. If we write its rate law, we've also written the rate law for the overall reaction. So again, we have two reactants here, the hydrogen peroxide and the iodide ion. So we're going to include both of those in the rate law. Both have no coefficient. This is bimolecular. So each one would have an exponent of 1, giving us a rate law that looks like that. That would be the rate law for step 1, and it would be the rate law for the overall reaction. And again, this is only because the slow step was the first step. Now, what happens when the slow step is not the first step? That's when you get to steady state approximation, and that is the last topic, 5.9. So again, these are all just flowing from one into the other. I could have treated them as separate topics, done separate sets of notes and practice on all of them, but it would have taken 4 times longer. So again, just piling them all into one because they are all interrelated. Steady state approximation is done when the slow step is not the first step. What we're going to do is we're going to highlight everything on the reactant side of the slow equation and everything that comes before it in every elementary step that comes before it. So if these are my 2 steps that I'm working with, I'm going to highlight the nitrogen monoxide and the NOBr2, and I'm going to highlight everything in step number 1. Now we're going to look to see what cancels out. Again, looking for things that are on the reactant side and the product side of the arrow. So if we look at this, the NOBr2 is on the product side and on the reactant side. So we are going to cancel those out. Finally, we're going to write the rate law like we would for any elementary step with what remains. We're going to write our rate constant as K prime because the rate constant for this rate law is not going to be the same as it is for any of the individual steps. It would be something unique and different, so the prime just indicates that. So it's going to be rate equals K prime. We have 2 NOs. It's going to be the concentration of NO squared. And we have 1 Br2. So it's going to be the concentration of Br2 to the first power. Looks like that. And again, this would be the rate law for our overall reaction. We could do individual rate laws for each step. They wouldn't be the same as this. So the rate law for the first step here would be rate equals K times the concentration of NO to the first power times the concentration of Br2 to the first power. We could write the rate law for this step. Rate equals K times the concentration of NO to the first power times the concentration of NOBr2 to the first power. And again, neither one of those rate laws is the same as this. So the K for this one is not going to be the same as either one of those rate laws. That's why we make it K prime. If you end up with a substance on the product side of an elementary step, once you're done doing all your cancellation, it is going to go in the denominator of the rate law. Something we haven't seen before because we haven't done this before. When we write the rate laws, we always end up looking at the reactant side and nothing but. But now, because we have to box in everything on the reactant side of our limiting step, our slow step, and everything that comes before it, we could have something on the product side of a previous step that doesn't cancel out. So again, we're going to go through the same process. I'm going to highlight everything in the slow step and everything that comes before it. We're going to cancel out what we can cancel out, and we're going to look at what we've got left. So we have two O3s, but they're on the reactant side. So we're going to put them in the numerator. But if we look over here, we have an O2 that's left on the product side. That O2, its concentration is going to go in the denominator of our rate law. So it ends up looking like this. And rate equals K prime, because we use K prime whenever we do steady state approximations. We have two O3s, so it's the concentration of O3 squared. They are on the reactant side of both steps, so they go on top. The oxygen is on the product side. There is no coefficient there, so it's just the concentration of oxygen to the first power, which I didn't bother to write in. But we put it in the denominator because it's on the product side. So there you have it. That's your video for the steady state approximation, the reaction mechanisms, the rate determining steps, the molecularity, all the stuff that's in topics 5.4, 5.7, 5.8, and 5.9.